At the edge of the oldest light in the universe, science encounters a silence it cannot yet cross. The cosmic microwave background carries echoes of a hot beginning, but behind it may lie something stranger, a burst of inflation, a quantum birth, colliding dimensions, an earlier cosmic cycle, or countless universes forming beyond our sight. Even the word before becomes uncertain, because time itself may have emerged with the Big Bang. As we follow these possibilities toward the limits of physics, consider supporting this journey with a like, subscribing for more calm explorations of the cosmos, and sharing the video with someone who enjoys questions without easy answers. Thank you sincerely for spending part of your day or night here. What time is it where you're listening, and where in the world are you watching from? Leave a comment and let this quiet community know. Now let us move beyond the oldest light and begin our search for what may have existed before the beginning. Before the universe has stars, atoms, light, or even the familiar flow of moments, there is a question that seems simple only because ordinary life gives it a shape. What comes before the Big Bang? The words appear to point backward, toward an earlier scene waiting behind the beginning, as if cosmic history were a long road and the first visible milestone merely concealed another stretch beyond it. Yet the deeper physics looks, the less certain that picture becomes. Time may not be an empty stage on which the universe appears. Time may be part of the universe itself, woven together with space, matter, and energy. If so, asking what happens before the beginning of the cosmos may resemble asking what lies north of the northernmost point. The question is not meaningless, but its familiar grammar may be trying to carry an idea farther than it can safely go. In daily experience, every event has a moment before it. Human thought is trained by sequences, causes, and changes. So the mind naturally expects the universe to follow the same order. There should be a previous state, then a transition, then the expanding cosmos. But the universe is not an object sitting inside a larger room with a clock already ticking outside it. Space is not merely the container of galaxies, and time is not simply a river flowing independently of everything that exists. According to general relativity, space and time form a single structure called space-time, and that structure responds to matter and energy. It can bend, stretch, expand, and perhaps reach boundaries where familiar notions of duration no longer apply. The Big Bang, in this framework, is not best understood as matter exploding outward from one location into pre-existing emptiness. It is the early condition of the entire observable universe, when space itself is expanding from a state that is far hotter and denser than anything found today. Every region now separated by immense cosmic distances belongs to that shared beginning. The expansion has no ordinary center within space, because it is space that changes. When this expanding history is traced backward, galaxies approach one another, matter becomes denser, radiation becomes hotter, and the known laws of physics are pushed toward conditions of increasing extremity. At first, the path is remarkably clear. Astronomers observe distant galaxies whose light is stretched toward longer wavelengths, a sign that cosmic space has expanded during the light's journey. The abundance of light elements agrees with a universe that once passes through a phase hot enough for early nuclear reactions. A faint field of microwave radiation fills the sky, carrying the cooled remnant of an age when the cosmos first becomes transparent. These observations support the broad picture of a hot, dense, early universe. They do not, however, provide a simple photograph of an absolute first instant. The farther the equations are extended into the past, the more severe the conditions become, until general relativity appears to produce a singularity, a point at which density and curvature grow without bound. A singularity is often described as the beginning of everything, but in physics it may instead signal the breakdown of a theory. The equations are being asked to operate in a realm where they are no longer complete. General relativity describes gravity and the large-scale structure of space-time with extraordinary success, while quantum theory describes particles in the smallest scales with equal power. Near the earliest conceivable phase, both should matter at once, yet no fully tested theory unites them. The apparent beginning may therefore be less like a discovered wall and more like a fog where the available map ends. This uncertainty changes the meaning of the question. There may be a genuine first boundary to time. There may be an earlier phase hidden by the limits of current theory. There may be a transition in which time, as presently understood, emerges from a deeper structure that does not behave like time at all. Each possibility preserves part of the original question while transforming the rest. If time truly begins with the universe, then there is no earlier moment in which nothing waits. There is no silent duration before creation, because duration itself is absent. The word before depends on time already existing, and without time it has no ordinary foothold. This does not mean that the universe appears after an infinite period of nothingness. An infinite period is still a period, and nothingness lasting for a duration already assumes a clock. Instead, the earliest boundary would be the place where temporal relations begin, with no prior interval behind them. The idea feels difficult because the mind tries to picture absence as a dark and empty scene. Yet darkness is a condition within space, and waiting is a condition within time. A true absence of space-time cannot be visualized as a room, a void, or a pause. Every image quietly restores the very framework being removed. Still, modern cosmology does not require that the hot Big Bang be the absolute beginning. Many models place an earlier process before the hot dense phase. The most influential is cosmic inflation, a brief period when space may expand at an extraordinary rate. In this picture, the universe begins the familiar hot phase only after inflation ends and its energy is transformed into particles and radiation. The hot Big Bang becomes not the birth of all reality, but a transition between cosmic regimes. Yet inflation does not settle the deeper mystery. It shifts the boundary farther back. What establishes the inflating state? Does inflation itself have a beginning? Does it arise from a quantum event, continue eternally in some regions, or emerge from conditions that have no classical time? Other approaches alter the picture more radically. Some quantum cosmological models suggest that the earliest universe does not possess a sharp temporal edge, but rounds off in a way that makes the distinction between space and time less definite. Some propose a bounce, where an earlier contracting cosmos reaches extreme density and begins expanding again. Some imagine repeating cycles, higher dimensional collisions, or a deeper quantum state from which space-time emerges. These ideas differ greatly in their mathematics and their evidence. None is established as the final account. Their shared lesson is quieter than any single claim the beginning may not resemble an event inside time. It may be a change in the nature of time, a boundary of time, or the emergence of time from something more fundamental. Even the word cause becomes uncertain there. In ordinary reasoning, a cause comes before its effect. A spark precedes a flame. A collision precedes a sound. But if time itself begins or changes character at the cosmic boundary, then the universe cannot have a cause in the usual temporal sense. A deeper explanation might still exist, perhaps in mathematics, physical law, probability, or a timeless relation, but it would not necessarily form a sequence with an earlier step followed by a later one. The desire for a first cause may therefore be reasonable, while the familiar image of causation is incomplete. Physics can ask how one state follows from another, which conditions permit a universe, and which models match observation. At the deepest edge, however, explanation may need a form that human intuition has never encountered in ordinary life. The calmest view is neither that the mystery is solved nor that it is forever unreachable. The known universe carries evidence from a very early age, and that evidence continues to sharpen. Ancient light, the distribution of galaxies, gravitational waves, and the behavior of fundamental particles may preserve clues about conditions far beyond direct sight. Each measurement narrows the field of possible stories. Yet no observation currently reaches an unquestioned first moment, and no accepted theory describes the origin of space-time with complete confidence. The phrase "before the Big Bang" therefore remains suspended between physics and language. It points toward a real scientific frontier, but it also exposes how deeply thought depends on time. At that frontier, the universe is not merely younger, hotter, and smaller. The categories used to describe existence begin to soften. Past and future may not yet stand apart. Cause and effect may not follow their familiar order. Space may not have settled into dimensions, and time may not flow as a sequence of moments. The mystery is not simply what occupies an earlier darkness. It is whether earlier, darkness, and occupation have any meaning there at all. The journey beyond the Big Bang begins with this restraint before searching for what comes first. Cosmology must discover whether first is a property the universe has always possessed. The Big Bang is often pictured as a flash at the centre of darkness, a colossal explosion throwing matter into an empty universe. The image is vivid, but it is misleading. There is no known central point from which everything flies outward, and there is no surrounding space waiting to receive the blast. The Big Bang describes an early state in which the universe itself is hot, dense, and expanding everywhere. Every large region, now separated by galaxies and immense distances, traces back toward that shared condition. The change is not matter racing through fixed space. It is the stretching of space between concentrations of matter. A simple comparison is sometimes made with marks on the surface of an inflating balloon. As the surface expands, every mark moves away from every other mark, yet none of the marks sits at the centre of expansion on the surface itself. The comparison is limited because the universe does not need to expand into a higher surrounding room, but it captures one essential point. Expansion belongs to the geometry of space, not to an explosion inside it. When cosmic history is followed backward, the distances between galaxies shrink, matter grows more crowded, radiation becomes more energetic, and the average temperature rises far enough back. Stars cannot exist because the universe is too hot for stable stars to form. Earlier still, atoms cannot remain intact. Electrons move freely through a glowing plasma of charged particles. Before that, atomic nuclei are broken apart, and at still greater energies even protons and neutrons are not yet stable composite objects. The early cosmos is not a tiny collection of familiar things compressed together. It is a changing field of energy and particles governed by physical conditions far beyond everyday experience. The phrase "hot Big Bang" refers to this prolonged early phase, not to a single explosion-like instant. It begins after whatever process establishes the hot dense state, and continues as expansion cools the universe through a sequence of transformations. In the earliest fractions of cosmic history that present theories can describe with some confidence, radiation dominates the energy of the universe. Particles appear, vanish, and exchange energy rapidly. Matter and antimatter are produced in pairs, while most pairs destroy one another again. Somehow, a slight excess of matter survives. The precise origin of this imbalance remains unresolved, but without it the later universe would contain far less of the material needed for stars, planets, and living systems. As expansion continues, temperatures fall, quarks become bound into protons and neutrons. Within the first few minutes, some of those particles combine into the nuclei of hydrogen, helium, and small amounts of other light elements. This process, called primordial nucleosynthesis, leaves a chemical signature that can still be measured. The observed abundance of helium and other light nuclei agrees closely with calculations based on a hot early universe. It is one of the great pillars supporting the Big Bang model, because the pattern is not easily explained by stars alone. Yet the universe remains opaque after these first nuclear reactions. Light cannot travel freely because charged particles scatter it repeatedly. The cosmos resembles a vast luminous fog, although no eye or surface exists from which it could be viewed. For hundreds of thousands of years, expansion steadily lowers the temperature. Eventually, electrons can remain attached to atomic nuclei. Neutral atoms form. Scattering becomes far less frequent, and light begins to move across space without constant interruption. That ancient radiation still fills the universe today. Expansion has stretched its wavelengths from the intense glow of the young cosmos into microwaves, producing the cosmic microwave background. This faint radiation is not light from the first moment. It is light released when the universe becomes transparent, long after the earliest hot stages. Even so, it offers a direct view of the cosmos in its infancy. Its temperature is almost uniform across the sky, with tiny variations that reveal slight differences in density. Over immense spans of time, gravity amplifies those small differences. Denser regions attract more matter, eventually forming galaxies, clusters, stars, and the broad web-like structure visible across the modern universe. The apparent smoothness of the early radiation and the delicate pattern of its variations are among the strongest clues that something important happens before the hot Big Bang phase. Regions now separated so widely that ordinary signals could not have crossed between them in the earlier standard expansion, nevertheless begin with nearly the same temperature. Cosmic inflation offers one possible explanation. Before the universe becomes hot and filled with ordinary particles, a much smaller region may expand extremely rapidly, stretching initial uniformity across an enormous volume. When inflation ends, the energy driving it may transform into radiation and matter through a process often called reheating. In this sense, the hot Big Bang is not necessarily the first event. It is the bright thermal aftermath of an earlier transformation. The distinction matters because it separates what observation strongly supports from what remains more uncertain. Evidence firmly indicates that the universe was once much hotter and denser, and has expanded and cooled for billions of years. The abundance of light elements, the cosmic microwave background, the recession of galaxies, and the growth of large-scale structure fit together within this framework. But the phrase Big Bang is used in more than one way. Sometimes it means the entire history of an expanding universe. Sometimes it means the hot dense phase. Sometimes it refers loosely to an imagined first instant. These meanings can blur, making the scientific picture seem more settled or more dramatic than it truly is. Modern cosmology is strongest when describing the evolution of the universe from an early hot state forward. It is less certain when asked what establishes that state, whether time begins there or whether another phase precedes it. There is also no need to imagine that all matter is packed into one point located somewhere in a larger emptiness. The observable universe may once have occupied an extremely small region compared with its present size, but the entire universe could have been far larger than the observable portion, perhaps even infinite. An infinite universe can expand while remaining infinite, just as an endless line can be stretched without acquiring an edge. In that case, the early cosmos is dense everywhere, not concentrated at one center. What becomes smaller in the backward description is the distance between places, not necessarily the total extent of all existence. This is one reason ordinary images struggle. Human experience treats objects as having edges, centers, and surroundings. The universe may possess none of these in the familiar sense. Even the observable universe has no physical wall. Its boundary is a horizon created by the finite age of cosmic history and the time light requires to travel. Regions beyond that horizon may exist, but their light has not reached the present location. The early hot phase therefore belongs not only to the matter now visible, but also, most likely, to regions forever beyond direct observation. The Big Bang is not an event seen from outside. There is no external viewpoint from which the whole expansion unfolds. Every observation occurs within the universe and carries information from the past along paths through space-time. Cosmology reconstructs that past by combining these signals with physical laws tested in laboratories and astronomical systems. The reconstruction is powerful, but it is not complete. As the equations approach earlier and more energetic conditions, uncertainties widen. Particle physics becomes less directly tested. Gravity must eventually be treated quantum mechanically, and the origin of the initial conditions remains unclear. Still, the hot beginning itself is not a guess added to an empty story. It is a conclusion supported by several independent traces, all pointing toward a younger cosmos that is smoother, denser, and hotter than the one seen now. The quiet transformation of the idea is therefore essential. The Big Bang is not a fireball erupting into darkness. It is the gradual emergence of a transparent, structured universe from an earlier state of heat and compression, with space expanding at every scale. Its oldest surviving light does not show a central blast. It shows an almost uniform sky, marked by minute variations that later become everything from galaxies to planets. Behind that light lies a still earlier realm where matter changes form. Forces may behave differently, and familiar descriptions begin to fail. The hot beginning is real, but it may not be the ultimate beginning. It is the first great chapter that observation can read with confidence, while the pages before it remain faint, incomplete, and deeply contested. Before the hot universe fills with particles and light, cosmology places a quieter and stranger possibility, a brief era in which space itself expands at an almost unimaginable rate. This proposed era is called cosmic inflation. It does not describe galaxies racing outward through an existing void. It describes the fabric of space increasing in scale so rapidly that regions once extremely close become separated by distances far greater than light could cross during the same interval. A small patch of the early cosmos may grow into a domain large enough to contain everything now visible, while retaining the imprint of conditions that existed when that patch was still microscopic. Inflation is not observed directly, and its precise mechanism remains unknown, yet it helps explain several puzzling features of the universe. The first puzzle is the remarkable uniformity of the cosmic microwave background. Ancient radiation arrives from opposite directions with nearly the same temperature. Even though those regions appear too widely separated to have exchanged light or heat during the ordinary hot expansion, inflation changes that history. Before the rapid stretching begins, the regions may lie close enough to influence one another and settle toward a common state. Inflation then carries them apart, preserving their similarity across a vast sky. The universe appears uniform not because distant regions coordinate after separation, but because they share a much earlier contact. The second puzzle concerns cosmic geometry. Measurements indicate that the observable universe is very close to spatially flat, meaning that on large scales it follows the familiar rules of flat geometry rather than showing strong curvature. Inflation naturally drives a large region toward apparent flatness, much as a small part of an enormous sphere looks nearly level. Any initial curvature is stretched over such a great distance that the visible portion becomes almost indistinguishable from a flat surface. The third puzzle involves unwanted relics. Some theories of high-energy physics suggest that the early universe could produce heavy and unusual particles in great abundance. Inflation would dilute these relics by spreading them through an enormous volume, leaving so few within the observable region that their absence no longer seems surprising. These successes make inflation attractive, but its most important contribution may be the origin of cosmic structure. At first, an inflating universe appears nearly smooth, yet quantum theory does not allow perfect stillness. Even the emptier state contains small fluctuations, temporary variations in fields and energy that arise from the uncertainty built into nature at microscopic scales. During inflation, these tiny fluctuations are stretched to astronomical size. Once inflation ends, they remain as slight differences in density from one region to another. Gravity works upon those differences over billions of years. Regions with slightly more matter attract still more, while regions with slightly less gradually become emptier. The delicate irregularities recorded in the cosmic microwave background may therefore descend from quantum fluctuations that once exist on scales smaller than an atom. Galaxies, stars, planets, and living systems eventually form around a pattern whose earliest seeds belong to the quantum world. The immense structure of the cosmos may begin in microscopic uncertainty. Inflation is usually associated with a field, a physical quantity present throughout space. The hypothetical field responsible is often called the inflaton, though the name does not identify a known particle or proven substance. In simple models, the inflaton holds a form of potential energy. While this energy dominates, it creates a pressure that drives accelerated expansion. Unlike ordinary matter, which becomes less dense as particles spread apart, the energy associated with the field can remain nearly constant for a time. More space then means more total field energy, and the expansion continues with extraordinary speed. This description does not mean the universe violates conservation laws in any simple sense. Energy conservation in an expanding space-time is more subtle than inside a fixed laboratory, because the geometry itself changes, and a single global total may not be defined in the usual way. Eventually, in most inflationary models, the field changes state. Its stored energy is released into particles and radiation, heating the universe and beginning the hot phase known as reheating. The word reheating can be misleading, because there may be no earlier ordinary thermal state that cools and warms again. It refers to the production of the hot particle-filled cosmos after the comparatively cold and empty inflationary stage. Space dominated by a smooth field becomes a dense mixture of interacting particles. The universe does not burst outward from a point, it changes character. Expansion continues, but no longer with the same extreme acceleration. Matter and radiation now govern the visible evolution, and the familiar hot Big Bang history begins. This transition makes inflation feel like a hidden prelude. Almost everything directly observed belongs to the aftermath, while the process itself lies behind an opaque barrier of energy and time. Its traces survive only indirectly, encoded in statistical patterns across the microwave sky, and perhaps in a background of primordial gravitational waves. Such waves would be ripples in space-time created during the rapid expansion. Their influence might leave a particular pattern in the polarization of ancient light. Searches continue, but no decisive signal has yet established a unique inflationary model. The absence of a confirmed signature does not disprove inflation, because many versions predict effects too weak for current instruments. It does, however, preserve uncertainty. Inflation is not one single theory with one exact prediction. It is a broad family of models, each using different field shapes, energy scales, durations, and endings. Some fit observations more comfortably than others. Some require conditions that seem finely chosen. Some continue forever in distant regions. Some begin only after another unexplained process. The theory solves problems, but it also creates new questions. What is the inflaton? Why does its energy have the required form? What places the universe in an inflationary state? What determines when inflation ends, if quantum fluctuations become the seeds of galaxies? Why do they possess the pattern that observations reveal? Measurements can restrict the answers, yet the fundamental mechanism remains open. There is also a deeper issue concerning the beginning. Inflation can occur before the Hot Big Bang, but it may not extend infinitely into the past. Several arguments suggest that a universe undergoing average expansion cannot be traced backward forever within the same classical description. This does not prove that all reality has an absolute beginning. It shows that inflation alone may be incomplete when pushed toward the deepest past. A prior quantum phase, a bounce, a boundary without ordinary time, or some other structure may still be required. Inflation moves the horizon of knowledge, but does not remove it. Even its duration is difficult to express in ordinary terms. The essential expansion may last far less than a fraction of a second. Yet because the scale grows exponentially, a tiny interval produces an enormous result. Exponential growth means that equal periods multiply size rather than merely adding to it. A region doubles, then doubles again, and each new doubling begins from something already larger. After enough repetitions, a patch smaller than any directly visible object can stretch beyond the observable universe. Neighbouring points are carried apart by the changing geometry between them, while local objects do not need to move through space faster than light. Relativity forbids material objects from outracing light through their immediate surroundings, but it does not impose the same limit on the expansion of space over great distances. During inflation, the distance between far separated points can increase extraordinarily quickly, without either point locally breaking the light speed limit. Inflation applies that principle under far more extreme conditions. The result is a cosmos smoothed, flattened, and enlarged almost beyond comprehension before ordinary matter takes center stage. Yet this apparent emptiness is not truly featureless. Quantum uncertainty remains, and the field-driving expansion may not decay everywhere at once. Some regions may stop inflating and become hot universes, while others continue expanding. That possibility leads toward eternal inflation and the idea of many cosmic domains. But even without taking that speculative step, the central mystery already deepens. The Hot Big Bang may emerge from a cold and nearly empty state. Fire may come after silence. Matter may arise from the energy of a field spread through space. The vast visible universe may descend from a region once unimaginably small, while its galaxies preserve enlarged traces of quantum fluctuations. Inflation gives cosmology a bridge between the microscopic and the cosmic, between uncertainty and structure, between a hidden prelude and the first light that can still be measured. But the bridge begins and ends in mist. Its broad shape agrees with much of what is observed, while its foundations remain concealed. Before the fire of the hot universe, space may expand in near darkness, carrying tiny fluctuations outward until they become the architecture of everything that follows. When inflation draws toward its end, the universe does not simply slow down and continue as an empty, enlarged space. The energy that drives the rapid expansion must change form. In many models, the field responsible for inflation begins to lose its smooth dominance and moves toward a lower energy state. Its stored energy is released into the fabric of the cosmos, creating particles, radiation, and heat. This transition is often called reheating. though the name can suggest a return to an earlier warmth that may never have existed. The inflating universe is likely cold in the ordinary sense, almost empty of familiar particles, yet filled with the energy of a field. Reheating is the moment when that hidden energy becomes a crowded and intensely active cosmic environment. It fills with the ingredients from which every later structure will emerge. Energy becoming matter is not a violation of physics. Modern theory treats matter and energy as different expressions of the same underlying reality. A sufficiently energetic process can create particles, provided the relevant conservation laws are satisfied. Particle accelerators demonstrate the same principle when collision energy produces new particles. The early universe carries this process to an extreme. Rather than a few collisions inside a machine, an immense field releases energy throughout space, producing a dense mixture of particles and their antimatter partners. At first, these particles do not form atoms or stable objects. They exist in a rapidly changing bath where creation and destruction occur almost continuously. Matter and antimatter meet and annihilate, returning their mass to radiation, while radiation creates new pairs when enough energy is available. The distinction between substance and light becomes fluid. Nothing remains fixed for long. The universe is governed by temperature, probability, and interaction. As reheating proceeds, the energy of the inflaton field may first produce a limited set of particles that then decay into many others. The details depend on how the field couples, or connects, to the known forces and particles. No single reheating model is confirmed, and the original field itself has not been identified. Yet any successful account must lead from a smooth inflationary state to the hot, nearly uniform mixture required by later cosmology. The release cannot be perfectly simple. It may involve oscillations of the field, rapid bursts of particle production, and a period during which the new particles gradually reach thermal equilibrium. Their energies gradually settle into a stable statistical pattern called thermal equilibrium. Once this state is established, the cosmos can be described by a temperature and by the kinds of particles able to survive at that temperature. The universe then enters the radiation-dominated era, where energetic particles and light control the expansion more strongly than ordinary matter. In this early heat, the forces of nature may not yet have the separate forms seen today. At accessible energies, electromagnetism, the weak nuclear force, the strong nuclear force, and gravity behave differently. At much higher energies, some of these distinctions may fade. Electromagnetism and the weak force are already known to be two aspects of a single electro-weak interaction under sufficiently energetic conditions. Earlier still, the strong force may also join them in a deeper unity, though this remains unconfirmed. As the universe expands and cools, symmetries break. When a physical symmetry breaks, the laws remain. But the universe settles into a state in which forces or particles behave differently. Cooling, therefore, does more than lower temperature. It changes the effective rules of the cosmic environment. One of the most important transitions involves the Higgs field, which exists throughout space. At extremely high temperatures, particles interacting with this field do not possess the same masses they display later. As the universe cools through the electro-weak transition, the Higgs field settles into a non-zero state. Certain particles then acquire mass through their interaction with it. Their mass arises from interaction with a field that fills the universe. Even this explanation is only part of the story. Most of the mass in protons and neutrons does not come directly from the Higgs field. It comes from the energy of the strong force binding quarks together. The matter of stars and planets is therefore largely stored interaction energy, confined within particles that appear solid only at much larger scales. The transformation from inflationary energy to matter is not a single step, but a sequence of conversions, phase changes, and binding processes. Among the unresolved stages is the origin of the excess of matter over antimatter. Reheating should naturally produce both in nearly equal amounts. The known laws allow particles and antiparticles to differ in subtle ways, but the observed universe contains far more matter than antimatter. If the two had remained exactly balanced, almost all would have annihilated as the cosmos cooled, leaving a universe dominated by radiation with scarcely any material from which stars could form. Instead, for reasons still uncertain, a tiny imbalance develops. For an enormous number of matter and antimatter particles that destroy one another, a small residue of matter survives. That residue becomes every galaxy, cloud, world, ocean, and living cell. Matter does not need to dominate by much at the beginning. It needs only to outnumber antimatter by a minute fraction before mutual annihilation removes almost everything else. The process that creates this imbalance is called baryogenesis, because baryons include protons and neutrons, the heavy particles at the centers of atoms. Several mechanisms have been proposed. Some involve unknown heavy particles whose decays favor matter slightly over antimatter. Some connect the imbalance to neutrinos, elusive particles that interact only weakly. Others place the crucial event during a phase transition in the early universe. The required general conditions are known, but the actual cosmic mechanism remains hidden. Ordinary matter therefore preserves an ancient, unexplained asymmetry. As cooling continues, the cosmic mixture changes again. Heavy unstable particles disappear, either decaying into lighter forms or annihilating with antiparticles. Quarks and gluons move freely for a time in a state called quark-gluon plasma. The strong force behaves unusually there because the temperature is too high for quarks to remain locked inside protons and neutrons. Later, as expansion lowers the energy, confinement begins. Quarks bind into composite particles, including the protons and neutrons that will eventually form atomic nuclei. This transition is not like tiny balls snapping together. Quarks are excitations of quantum fields, and the binding energy of the strong interaction becomes an essential part of the resulting mass. Protons are restless quantum systems whose mass largely reflects binding energy. Even after protons and neutrons form, the universe is still too hot for atoms. Collisions are violent enough to break complex structures apart. Neutrinos gradually stop interacting frequently with the surrounding plasma and begin traveling almost freely through space. Electrons and positrons continue to annihilate, adding energy to the sea of radiation. A small population of electrons survives because the earlier matter excess requires enough negative charge to balance the positive charge of protons. The universe carries no deliberate plan. Yet conservation laws and interaction strengths guide the mixture toward the ingredients of later chemistry. Within the first minutes, some protons and neutrons bind into light nuclei, mainly hydrogen and helium. Much later, electrons join those nuclei to form neutral atoms. Later still, gravity gathers gas into stars, where heavier elements are forged. But the essential transition begins much earlier, when the smooth energy behind inflation becomes particles and heat. Every later object depends on that conversion. The iron in a planet, the carbon in a cell, and the light from a star trace their ancestry through stellar furnaces and ancient gas, then farther back through nuclei, quarks, radiation, and finally the release of energy at the end of inflation. Reheating is therefore one of the most consequential hidden events in cosmic history, yet it leaves no direct image. Its evidence is indirect. Carried by the success of the hot Big Bang model, and by possible traces in the distribution of matter and primordial waves, the exact temperature reached, the particles first produced, and the duration of the transition remain uncertain. A different inflationary model may lead to a different reheating history, and those differences may affect later observations. The end of inflation is not merely where rapid expansion stops. It is where an almost empty universe becomes fertile with physical possibility. Fields begin to transfer energy, symmetries break, particles gain mass. Matter and antimatter nearly erase one another. A tiny imbalance survives, and from that narrow remainder the visible universe takes shape. The transformation is violent in energy but quiet in meaning. No stars ignite, no planets turn, and no atoms yet hold together. Still, the basic ingredients of structure are present. Emptiness has not produced something from absolute nothing. One form of physical reality has become another, and the cosmos has crossed from expansion driven by a hidden field into an age of heat, particles, and change. The question of what begins inflation appears almost immediately after inflation is used to explain the early universe. A period of rapid expansion can smooth space, flatten its geometry, and stretch quantum fluctuations into the seeds of galaxies. But those successes do not reveal why the process starts. They describe what inflation may do once it exists. They do not identify the deeper condition that brings an inflating state into being. In many models, inflation depends on a field resting high on a landscape of potential energy. The field changes slowly enough that its energy remains nearly constant while space expands at an accelerating rate. This is mathematically possible, and it can produce patterns that agree well with observation. Yet the picture quietly assumes an unusual starting point. The field must begin in a suitable region of its potential. Its motion must be slow enough. Other forms of energy must not overwhelm it. The surrounding geometry must permit inflation to persist. Each requirement turns the beginning of inflation into a problem of initial conditions. A theory may explain how inflation continues while leaving unexplained why the universe enters the right state at all. One possibility is that suitable conditions arise naturally from quantum uncertainty. At extremely small scales, fields do not sit with perfect stillness. Their values fluctuate, and space-time itself may possess quantum behavior. An inflating patch could emerge from a rare fluctuation, a tunneling event, or a transition from a more primitive quantum state. In such models, inflation does not require a classical universe already waiting with a clock and a smooth field. It may appear as part of the process through which classical space and time become defined, but this idea immediately raises another difficulty. Quantum tunneling is normally described as a transition between states within an existing physical framework. When it is applied to the origin of space-time, the usual background is missing. The mathematics can still assign probabilities to different cosmic histories, yet the meaning of those probabilities becomes obscure. Probability usually refers to repeated possibilities, an ensemble of systems, or uncertainty about an event. At the origin of a single universe, it is not clear what counts the alternatives or what establishes the rule by which one history is favoured over another. The mystery moves from the cause of inflation to the foundation of probability itself. Another possibility is that inflation begins within an earlier universe. A contracting phase may compress matter and fields until a bounce occurs, after which expansion and inflation follow. A higher dimensional collision may release energy and create an inflating region. A universe may emerge from an earlier cycle, carrying altered but not entirely erased conditions from a previous cosmic age. These proposals give inflation a prehistory, but they also inherit new questions. What causes the bounce? Why does the collision occur? What prevents the earlier phase from collapsing into a singularity? How stable are repeated cycles? Each mechanism can move the apparent beginning farther back without reaching an ultimate explanation. The chain of causes lengthens, while its first link remains hidden. Even when inflation begins, its duration is uncertain. Successful models usually require enough expansion to make the observable universe smooth and nearly flat. This is often expressed through repeated exponential growth, measured by how many times the cosmic scale multiplies by the same factor. The visible universe needs many such intervals, but the minimum is not a universal number because it depends on the energy of inflation, the details of reheating, and the later expansion history. Inflation may last only slightly longer than required, or it may continue for an enormously greater span. The portion that becomes the observable universe records only a limited segment. Anything that happens much earlier is stretched beyond the present horizon, leaving little or no direct trace. Inflation can therefore erase evidence of its own beginning. The same process that explains why the universe looks simple may hide the conditions that establish that simplicity. This loss of information creates a peculiar scientific boundary. The cosmic microwave background preserves patterns from the final stages of inflation, because fluctuations leaving the relevant scale near the end can later reappear as variations in ancient light. But fluctuations from a much earlier stage are carried to distances larger than the region that can ever be observed. They may exist beyond the horizon, yet no signal from them reaches the present. The universe could inflate for a modest duration, or for a vast and almost timeless interval before the observable modes are produced, and both histories might lead to nearly the same sky. The beginning becomes not only theoretically uncertain, but observationally concealed. The end of inflation is another open question. In the simplest models, the driving field slowly moves down its potential until the conditions for accelerated expansion fail. It then oscillates near a lower energy state and transfers energy into particles. This gradual departure is called slow-roll inflation, because the field changes gently while expansion remains rapid. The name suggests a smooth descent, but the underlying field landscape is hypothetical. Different shapes produce different predictions for the strength and pattern of primordial fluctuations. Observations rule out some simple forms and favor others, yet they do not identify a unique potential or a known particle. Inflation may end because one field reaches a critical value. It may end because a second field becomes unstable. It may end through a sudden phase transition, forming bubbles of a new state that expand and collide. It may decay unevenly, with some regions reheating while others continue to inflate. Every ending changes the later universe in subtle ways. It influences the temperature after reheating, the species of particles produced, and possibly the balance between matter and antimatter. An incomplete account of the ending therefore leaves gaps throughout the story that follows. There is also a tension between a graceful exit and eternal continuation. A model must allow inflation to stop in the region that becomes the visible universe. Yet quantum fluctuations may sometimes push the field upward, while classical motion carries it downward. In places where upward fluctuations dominate, inflation can continue. Space expands so rapidly there that the inflating volume grows even as separate regions stop and form hot universes. The process may become eternal toward the future, not because every location inflates forever, but because some expanding regions always remained. This possibility changes the question of duration. Inflation may have a local ending while the larger process has no global ending. Each reheated domain becomes a cosmic region with its own observable history, separated from others by expansion too great to cross. If this picture is correct, the Hot Big Bang is a regional event rather than a universal one. Yet eternal inflation remains difficult to test. The other regions lie beyond causal contact, and attempts to assign probabilities across an endlessly growing collection of domains face a serious problem known as the measure problem. Different ways of counting the infinite regions can produce different predictions. Without a natural rule for comparison, the theory may struggle to say what a typical observer should expect to see. Even the beginning of eternal inflation is uncertain. A process that continues without end toward the future does not necessarily extend without end into the past. Mathematical results suggest that a space-time with sufficient average expansion cannot be complete in the backward direction under broad conditions. This does not prove creation from nothing, and it does not rule out every past eternal model. It indicates that the inflationary description alone cannot usually provide the whole history. Some earlier boundary or different physical regime is still required. The arrow points backward again, toward quantum gravity and conditions where classical spacetime may dissolve. The unanswered trigger is therefore more than a missing detail inside an otherwise finished theory. It marks the point where cosmology confronts the origin of its own explanatory framework. Inflation can turn a small, smooth patch into an immense universe. But it does not yet explain the patch. It can magnify quantum fluctuations, but it does not fully explain the quantum state from which they arise. It can end by reheating space, but the mechanism remains unknown. It can continue eternally in a larger setting, but that setting creates new problems of prediction and beginnings. The theory is powerful because it connects a hidden early process to measurable patterns. It is incomplete because many distinct mechanisms can produce similar patterns. The calm sky of ancient radiation may carry evidence that inflation occurs, while withholding the identity of the field, the reason it starts, the total time it lasts, and the event that ends it. At the deepest level, inflation is both an answer and a postponement. It explains how the universe becomes large, smooth, and structured, then leaves open why any inflating reality exists to begin The oldest light in the universe does not arrive as a blaze. It comes as a faint microwave glow spread across the whole sky, perfectly uniform. This radiation is called the cosmic microwave background, and it is the nearest thing cosmology possesses to an image of the young universe. It does not show the first instant or the birth of space-time. It comes from a later age, when the cosmos is already hundreds of thousands of years old. Yet because no earlier light travels freely to the present, this gentle background marks the deepest visible surface in ordinary electromagnetic radiation. Beyond it lies a universe hidden by its own ancient opacity. In the early hot phase, matter exists as a plasma, a glowing mixture of electrons, atomic nuclei, and light. Photons move constantly, but they cannot travel far. Free electrons scatter them in every direction, much as droplets scatter light inside a dense fog. The universe is full of radiation, yet it is not transparent. As space expands, the plasma cools. Eventually, electrons remain bound to nuclei long enough to form neutral atoms, mainly hydrogen and helium. With far fewer free charges available to scatter light, photons begin to travel across great distances. This transition is often called recombination, though it is the first lasting combination of electrons and nuclei rather than a second union. The released light crosses the universe from that moment onward. Expansion stretches its wavelength, lowering its energy until the original warm glow becomes microwave radiation. What once belongs to a universe with a temperature of several thousand degrees now appears only a few degrees above absolute zero. The cooling does not erase the photons' history. Their wavelengths record the expansion of space, and their distribution preserves the conditions of the matter from which they last scatter. The result is a cosmic fossil, carried not by rock but by light. When sensitive instruments map this radiation, the sky first appears almost featureless. its temperature changes by only tiny amounts from one direction to another. That smoothness is itself a major clue. Widely separated regions possess almost the same temperature, even though a simple hot Big Bang model does not allow enough time for them to exchange energy and settle into balance. Inflation offers a possible solution by placing those regions in contact before stretching them far apart. The uniformity of the microwave background therefore supports the idea that the visible universe grows from a much smaller, smoother domain. Still, perfect smoothness would produce no galaxies. If matter begins with exactly the same density everywhere, gravity has no preferred places in which to gather it. The microwave background contains the required imperfections. Its slight temperature variations correspond to small differences in density and motion. Some regions hold a little more matter, some a little less. And radiation shifts in energy as it climbs through or falls into shallow gravitational wells. These variations are extraordinarily small, yet they become the foundation of cosmic structure. Over billions of years, gravity amplifies them. Slightly denser regions draw in more material. Dark matter forms invisible frameworks. Gas settles into those frameworks, cools, and eventually ignites the first stars. Galaxies gather along vast filaments, while emptier regions become broad voids. The crowded modern cosmos grows from a pattern once visible only as minute changes in an ancient glow. The pattern is not random noise without form. It contains preferred angular scales and statistical relationships that reveal how sound waves move through the early plasma. Before atoms form, gravity pulls matter inward, while radiation pressure pushes it outward. The struggle creates acoustic oscillations, waves of compression and rarefaction moving through the hot mixture. Recombination freezes a snapshot of those waves into the microwave background. Their sizes and strengths reveal the contents and geometry of the universe. They show how much ordinary matter exists, how much dark matter is present, how rapidly expansion proceeds, and how close large-scale space is to flat. The sky becomes a record of physical conditions, written in temperature differences too small for unaided senses to notice. Satellites and ground-based observatories map this record with increasing precision. The COBE mission first measures the background as an almost perfect thermal spectrum and detects its tiny variations across the sky. WMAP later produces sharper maps, allowing cosmologists to estimate the age and composition of the universe with greater confidence. The Planck mission examines still finer detail, measuring temperature and polarization over much of the sky. Polarization describes the preferred orientation of the light's electric field. It forms when radiation scatters in an uneven environment. Some polarization traces the density waves already visible in temperature maps. Another possible pattern could carry evidence of gravitational waves generated during inflation. Such a discovery would open a much earlier window, because primordial gravitational waves may preserve information from the inflationary era. Yet the search is difficult. Dust within the Milky Way also polarizes microwave light, and its signal can resemble the sought pattern. A claimed detection can fade when galactic foregrounds are measured more carefully. The quiet background demands patience, because the desired imprint may be weaker than the dust between nearby stars, even without a confirmed inflationary wave signal. The observed microwave pattern agrees strikingly well with a universe that begins with nearly scale-independent, almost Gaussian fluctuations. Scale-independent means that variations have a similar strength across a broad range of sizes. Gaussian means that their distribution follows a simple statistical form, with extreme deviations becoming increasingly rare. Many inflationary models naturally produce fluctuations of this kind. The agreement is important, but it is not unique proof. Different early universe mechanisms may imitate parts of the same pattern, and inflation itself includes many possible versions. The microwave background narrows the field, excludes some ideas, but it does not identify one final history. Its evidence behaves like a preserved shadow. It reveals the shape of processes that occur earlier, while the processes themselves remain beyond direct view. The ancient light also contains signs of later events. As photons travel through the evolving universe, they pass near galaxies, clusters, hot gas, and changing gravitational fields. Their paths bend through gravitational lensing. Some scatter from energetic electrons in galaxy clusters, shifting slightly in energy. Large-scale structures alter the radiation in subtle ways. These later effects allow the background to act as a light source behind the visible cosmos, illuminating matter that would otherwise be difficult to map. By separating the original pattern from changes acquired during its journey, cosmologists reconstruct both the early universe and part of the history that follows. Yet the reconstruction has limits. The microwave sky represents a surface of last scattering, not a solid shell surrounding one special location. Every observer anywhere in the universe has a different such surface centered on that observer. The radiation comes from all directions because the young universe fills all space. The apparent sphere exists because light from a particular distance has only now had time to arrive. Regions beyond it are not necessarily empty, and the surface itself is not the edge of creation. It is the edge of transparency. Earlier photons remain trapped and repeatedly scattered, erasing any simple image of deeper times. To reach beyond that barrier, cosmology must rely on messengers other than ordinary light. Neutrinos from the early universe may form a background older than the microwave radiation. Though detecting it directly is extraordinarily difficult, gravitational waves may travel almost untouched from even earlier eras, but their primordial signal has not yet been securely found. The distribution of light elements provides another indirect record, while particle experiments test the laws that govern extreme energy. Each method approaches the hidden past from a different direction. None yet opens a clear view of the beginning. The cosmic microwave background therefore stands at a threshold. In front of it lies the visible history of atoms, stars, galaxies, and expanding structure. Behind it lies a bright but opaque plasma. Then still earlier transitions where nuclei, particles, and fields change their behavior. Farther back waits the proposed inflationary era, known only through traces stretched across the later sky. The faint glow does not answer what comes before the Big Bang. It does something more careful. It demonstrates that the early universe leaves evidence, that ancient conditions can survive as patterns, and that speculation must face measurement. The sky carries a baby picture of the cosmos, but the picture also contains enlarged fingerprints of processes that may occur before light travels freely. Its near uniformity suggests a hidden smoothing. Its small irregularities become the seeds of structure. Its polarization may yet preserve ripples from an era of rapid expansion. In a universe filled with distance and silence, the oldest light remains a quiet witness. It reaches the present after crossing almost the whole of cosmic history, bringing no direct scene from the beginning, only a delicate pattern that points beyond itself toward a deeper and still invisible past. At the earliest edge of cosmic history, two of the most successful theories in science begin to speak different languages. General relativity describes gravity as the curvature of space-time. Matter and energy tell space-time how to bend, while curved space-time tells matter how to move. Quantum theory describes a very different realm. It governs particles, fields, uncertainty, and the strange behavior of nature at extremely small scales. In ordinary quantum physics, particles and fields change within a background of space and time that is already present. In general relativity, that background is not fixed. It is a physical object that can stretch, ripple, and collapse. Near the beginning of the universe, these two descriptions can no longer remain separate. Matter is compressed to extreme density. Distances become extraordinarily small, and space-time itself must behave quantum mechanically. The place where the theories should meet is exactly where neither provides a complete account alone. This is why the earliest moment cannot be understood simply by extending familiar equations backward without limit. General relativity predicts that density and curvature may become infinite at singularity. Quantum theory warns that the classical picture should break down before such infinities are reached. A singularity may therefore be less a physical object than a sign that the mathematical description has crossed beyond its domain. The universe does not necessarily begin as an infinitely dense point. It may enter a regime where the ideas of point, distance, duration, and smooth geometry no longer have their ordinary meaning. A successful theory of quantum gravity would describe that regime. No such theory has yet been confirmed by experiment, but several approaches attempt to reveal what lies beneath classical spacetime. One approach begins with the insight that gravity may need to be quantized like the other forces. In quantum field theory, particles are excitations of fields. Gravity might also possess a quantum particle, often called the graviton, representing a small ripple in the gravitational field. This idea works well when gravity is weak and space-time is nearly fixed, but severe problems appear at very high energies. Straightforward calculations produce infinities that cannot be controlled by the usual methods. Gravity changes the stage on which the calculation occurs, and the distinction between field and background begins to dissolve. A deeper framework is required. String theory proposes that the fundamental ingredients of nature are not point-like particles but tiny vibrating strings. Different vibration patterns appear as different particles, and one pattern behaves like a graviton. Gravity emerges naturally, while extra spatial dimensions and extended objects called branes become part of the mathematics. In some models, the Big Bang can be interpreted as a collision between branes or as a transition within a larger dimensional structure. Yet the theory allows a vast range of possible solutions, and no direct experimental evidence has selected one as the description of the universe. Its mathematical richness offers possibilities, but the cosmic beginning remains unsettled. Another approach, called loop quantum gravity, attempts to quantize space-time itself without replacing particles with strings. In this picture, space may possess a discrete structure at the smallest scale. Areas and volumes come in tiny units, rather than varying without limit. Smooth space-time emerges only when these quantum pieces are viewed on much larger scales. Much as a continuous fabric appears smooth, even though it is woven from individual threads. Applied to cosmology, related models sometimes replace the classical singularity with a bounce. As a contracting universe reaches an extreme but finite density, quantum effects create a repulsive influence that prevents infinite collapse. Expansion then begins. The Big Bang becomes a bridge from an earlier contracting phase rather than an absolute beginning. This result is intriguing, but it depends on simplified models and has not been established as the history of the real cosmos. Other approaches treat space-time as something that emerges from more fundamental relationships. In this view, space may not be a basic ingredient at all. It may arise from patterns of quantum entanglement, the deep connection by which separated quantum systems share a single state. Geometry could be a large-scale expression of information and correlation. If the connections change, the shape of space changes. Time might also emerge from relationships among quantum states rather than flowing as an independent background. At the deepest level, the universe could be described without ordinary space or time, while the familiar space-time of general relativity appears only in a suitable limit. This possibility transforms the question of what comes before the Big Bang. If time is emergent, the underlying state does not need to exist earlier in a temporal sequence. It may provide the structure from which temporal order itself develops. Some quantum cosmological proposals describe the universe through a wave function. In ordinary quantum mechanics, a wave function contains the possible outcomes for a system and the probabilities associated with them. Applied to the whole universe, the idea becomes difficult because there is no external observer, no outside clock, and no larger laboratory. The universe includes every measuring device and every physical reference frame. Its quantum state must therefore describe possible geometries, fields, and histories from within. Certain equations used in this approach do not contain time in the familiar form. The apparent disappearance of time is known as the problem of time. It suggests that the flow experienced in the classical world may arise only through correlations between parts of the universe. One part behaves as a clock relative to another, creating an effective sequence even when the fundamental equation is timeless. Near the cosmic origin, that sequence may fade. A universe can then have a boundary without a moment before it, or a transition from a quantum state in which past and future are not yet distinct. One proposal replaces the sharp beginning with a smooth geometry where time behaves more like a spatial direction near the earliest boundary. On a sphere, there is a southernmost point but no edge beyond it. Similarly, cosmic history might close smoothly without requiring an earlier instant. Another proposal imagines the universe tunneling into a classical state from a quantum condition. The phrase "from nothing" is sometimes used, though it does not mean absolute philosophical nothingness. The model still relies on laws, quantum rules, and mathematical structure. It describes the absence of classical space-time, not the absence of every possible form of reality. It changes the level at which the question is asked. Observations may eventually distinguish among some of these ideas. Quantum gravity could leave traces in primordial gravitational waves, unusual patterns in the cosmic microwave background, or small departures from the simplest inflationary predictions. A bounce might create characteristic correlations across very large scales. Extra dimensions could influence particle behavior or gravity at short distances. Black hole physics may reveal how space-time stores information. Yet the expected effects are often extremely weak, hidden behind later cosmic evolution, or associated with energies far beyond any present experiment. The search therefore moves between cosmology, particle physics, mathematics, and the study of black holes. Each field approaches the same boundary from a different direction. General relativity reveals that space and time are dynamic. Quantum theory reveals that nature is uncertain, discrete in some measurements, and governed by amplitudes rather than definite classical paths. A final account must preserve the proven successes of both, while changing their foundations enough to remove the conflict. It must explain how smooth space-time emerges, why gravity behaves classically at large scales, and what replaces the singularity at the beginning. It must also connect to observations rather than remaining only an elegant possibility. Until that happens, the origin of the universe remains suspended between two incomplete views. The classical theory carries history backward until geometry becomes infinitely strained. The quantum theory suggests that no exact classical history exists there at all. Somewhere near that boundary, space may become granular, dimensions may change, geometry may emerge from information, or time may lose its separate identity. The Big Bang may be a beginning, a bounce, a transition, or the first classical page of a deeper quantum story. The mystery is not merely what matter does at extreme density. It is what space and time are when they can no longer be assumed. At that quiet frontier, the universe approaches a condition in which location, duration, and cause may all arise together, and the search for what comes before becomes a search for the origin of before itself. Inflation may end in the region that becomes the observable universe, yet it does not necessarily end everywhere. This possibility leads to one of the most unsettling extensions of modern cosmology, eternal inflation. In this picture, the process of rapid expansion continues without limit in some parts of a larger cosmic structure, even while other regions stop inflating, release their energy, and become hot universes. The result is not a single beginning followed by one expanding cosmos. It is an ongoing landscape in which new cosmic domains repeatedly emerge from an inflating background. Each domain begins with its own version of a hot Big Bang, while the wider process continues beyond it. The word eternal refers mainly to the future. It does not guarantee that inflation stretches infinitely into the past. It means that once the process enters the right regime, the total inflating volume grows faster than inflation can end. Local endings occur, but the larger system never finishes. To understand how this happens, inflation must be viewed as both a classical and a quantum process. Classically, the field driving inflation moves down its potential toward a lower energy state. When it reaches the proper region, inflation ends and reheating begins. Quantum theory, however, adds fluctuations. In some patches, the field moves slightly farther down, bringing inflation closer to its end. In others, it fluctuates upward, delaying the transition. Because space expands exponentially, the patches that continue inflating create more volume at an extraordinary rate. Even if many regions stop, the surviving inflating regions can multiply faster than they disappear. The process reproduces itself. Each newly enlarged region contains further patches where the field fluctuates, and some of those continue. Inflation ends again and again, yet it never ends everywhere at once. The hot universe familiar to observation would then occupy only one reheated domain inside a much larger structure. This domain is sometimes compared with a bubble, though the comparison can be misleading. It is not necessarily a round object expanding through an ordinary surrounding space. The geometry is shaped by inflation itself, and the boundary between an inflating region and a reheated region may behave in ways that have no everyday counterpart. Within a bubble universe, expansion, cooling, particle formation, and cosmic structure proceed according to local conditions. Beyond its observable horizon, other domains may exist, but the intervening inflation separates them so rapidly that communication becomes impossible. Light from one region never reaches another if space between them expands too quickly. Each bubble can appear complete from within, with no visible sign of the process that produces it. The multiverse in this context is not a collection of universes arranged like planets in a larger room. It is a network of causally separated regions generated by the dynamics of space-time and fields. Some may form earlier, some later, though the meaning of a single global time becomes uncertain. In relativity, different choices of cosmic slicing can disagree about which distant events happen at the same moment. Eternal inflation magnifies this difficulty. There may be no unique clock that orders every bubble and every inflating region. This makes even the act of counting universes difficult. If the process produces infinitely many domains, then every allowed type may occur infinitely many times. Comparing their frequencies requires a rule for handling infinity. A naive count gives infinity divided by infinity, which has no unique value. Cosmologists call this the measure problem. Different ways of defining a cutoff, choosing a time coordinate, or weighting regions can lead to different predictions. A theory that produces everything may struggle to say what is likely. Without a well-justified measure, the multiverse risks becoming too flexible. because almost any observation could be said to occur somewhere. A model must connect the space of possible universes to testable probabilities for the one observed. Eternal inflation becomes especially significant when combined with theories that allow many possible low-energy states. String theory, for example, appears to contain a vast landscape of solutions, each corresponding to different ways that extra dimensions can be arranged and different values for physical properties. Inflation might populate portions of this landscape by creating domains that settle into different states. One universe may have a stronger force, another a different particle spectrum, another a vacuum energy unlike the one measured locally. Many domains may never form stable atoms or long-lived stars. Some may collapse quickly, others may expand too rapidly for matter to gather. A small subset may permit complex structures. In such a picture, the laws observed within one universe are partly environmental. They resemble local conditions selected from a wider range rather than a single unavoidable outcome. This possibility leads to anthropic reasoning. Any observers capable of measuring a universe must arise in a region compatible with their existence. A universe without stable matter contains no one to notice its instability. A universe that expands too quickly to form galaxies contains no astronomers to wonder about expansion. Therefore, observation is automatically biased toward domains where complexity can emerge. This does not mean life causes the laws of physics. It means the act of observing selects a restricted class of environments from the full set that may exist. The reasoning can help explain why certain constants appear finely balanced, but it remains controversial. Some physicists view it as a legitimate consequence of a large multiverse. Others worry that it weakens the search for deeper laws by replacing explanation with selection. The difference depends on whether the multiverse can make quantitative predictions that observations can test. Direct detection of another bubble universe is unlikely, but not necessarily impossible in principle. If two bubble regions collide early in their histories, the event might leave a pattern in the cosmic microwave background, perhaps a circular disturbance or a directional asymmetry. Searches for such features have not produced convincing evidence. The absence of a signal does not rule out eternal inflation, because collisions may be rare, weak, or hidden beyond the observable horizon. Primordial gravitational waves and the detailed statistics of cosmic fluctuations might also constrain the kinds of inflation capable of becoming eternal. Yet no observation currently establishes that other universes exist. The idea remains an implication of certain models rather than a confirmed discovery. There is also the question of beginnings. A process can be endless toward the future and still require an earlier boundary. Mathematical arguments indicate that spacetimes with persistent average expansion are generally incomplete when traced backward. This suggests that inflation cannot by itself describe an infinite past under broad conditions. Something else may precede it: a quantum origin, a bounce, a static phase, or a framework in which the concept of past time changes. Eternal inflation multiplies cosmic beginnings without explaining the beginning of the multiplying process. It turns one mystery into a hierarchy. Each bubble has a local origin in reheating. The inflating background has its own deeper origin, and whatever establishes that background remains unknown. The idea also changes the scale of cosmology, though the physics itself remains indifferent. The observable universe is already vast, containing distances and structures far beyond direct reach. Eternal inflation makes that visible immensity only one small region within a process that may produce endlessly many domains. Every galaxy seen through telescopes belongs to one local cosmic history. The entire observable sky could be a tiny patch inside a bubble whose full extent remains inaccessible. Beyond it, expansion may continue. New regions may cool, and other histories may unfold without ever sharing information. There may be no central universe, no first bubble, and no final generation. Yet the grandeur of the picture should not be mistaken for evidence. Its scale comes from mathematical extrapolation. The same equations that successfully describe inflation over a limited range may be uncertain when extended without bound. Quantum gravity may alter the process. Unknown principles may prevent eternal behavior. The inflating field may not exist in the required form. A complete theory may replace the multiverse with something simpler. Scientific caution therefore remains essential. Eternal inflation is not fantasy, because it grows from real equations and serious attempts to understand the early universe. It is not established fact, because the crucial evidence remains indirect and incomplete. Its importance lies in how naturally it can arise once quantum fluctuations act inside an exponentially expanding space-time. A mechanism introduced to explain one hot beginning may generate many. The end of inflation becomes a local event, not a universal conclusion. The Big Bang becomes one opening among countless openings, each concealed from the others by the expansion that creates them. The universe then ceases to be the whole stage and becomes one illuminated region within a much larger, mostly invisible process. At the edge of present knowledge, inflation does not merely precede fire. It may continue beyond every horizon, quietly producing new fires without end. If eternal inflation produces many cosmic domains, the question soon shifts from how many universes exist to whether they all obey the same physical rules. In the simplest picture, every region inherits identical laws and differs only in the arrangement of matter. Yet several theories allow a more radical possibility. The underlying framework may be shared, while the values that shape local physics vary from one domain to another. The strength of forces, the masses of particles, the energy of empty space, and the form of hidden dimensions may settle differently when each region leaves inflation. What appears within one universe as a fixed law of nature could then be a local outcome selected from a broader range of possible states. A deeper theory may permit many stable solutions, each producing a different low-energy world. Once a cosmic region cools into one of those solutions, its properties become effectively fixed. Observers inside it experience those values as permanent constants because the surrounding vacuum state determines how particles and forces behave. A vacuum in quantum physics is not absolute emptiness. It is the lowest energy state of fields, and different vacuum states can carry different physical properties. If inflation creates domains that settle into different vacua, the same deep theory may generate many outwardly different universes. Gravity may be stronger in one, electrons may be heavier in another. Nuclear reactions may proceed differently elsewhere. Many such worlds could be sterile, brief, or almost structureless. A smaller set might allow long-lived complexity. The familiar universe depends on a delicate network of relationships. Stars form because gravity gathers gas, while pressure and heat resist collapse. Nuclear forces allow protons and neutrons to bind inside atomic nuclei. Electromagnetism holds electrons around nuclei and makes chemistry possible. Particle masses influence which reactions occur and how much energy they release. The energy associated with empty space affects whether cosmic expansion accelerates too quickly for galaxies to assemble. Changing one value does not merely adjust one isolated feature, it sends consequences through the entire system. A stronger force may alter stellar lifetimes, element production, and planetary conditions together. A heavier particle may destabilize atoms or close a pathway needed for nuclear burning. Carbon and oxygen illustrate this interdependence. Stars build heavier elements through nuclear reactions in their cores. The production of carbon depends on the behavior of helium nuclei and on an excited state of the carbon nucleus that makes a crucial reaction far more likely Oxygen then forms through further reactions, but not so efficiently that nearly all carbon disappears. Small changes in nuclear properties could alter the balance. This does not prove that the constants are chosen for life, and some variation may be tolerated. Stable atoms require charges and masses to stand in suitable relationships. Long-lived stars require gravity and nuclear physics to cooperate. Complex structures need enough time to form before stars die, or expansion carries matter too far apart. The apparent fit between these conditions and the existence of observers is often called fine-tuning. It identifies sensitivity, not intention. A parameter appears fine-tuned when the observed value lies within a range that permits galaxies, stable nuclei, or chemistry. But the conclusion depends on which parameters are varied. What other quantities are held fixed, and what counts as a viable universe? Changing several values together may preserve structures that vanish when one value changes alone. Fine-tuning is therefore a genuine puzzle, but its exact severity remains difficult to measure. One response is that a deeper theory eventually determines every constant uniquely. The values then have no freedom to vary, even if their necessity is not yet understood. Another response is that many sets of values occur across a multiverse. Most domains fail to form complex structures, while a minority possess conditions compatible with observers. Any observer necessarily finds itself in one of that minority. This selection effect is called the anthropic principle in its cautious form. It does not claim that the universe exists for observers. It states that observed conditions cannot be treated as a random sample from all possible conditions, because observations occur only where observers can arise. A successful anthropic explanation needs a theory describing which constants can vary, how often different values arise, and which values permit complex structure. Eternal inflation may supply many domains, while a landscape of vacuum states supplies many possible laws. Yet the measure problem makes their relative abundance uncertain. The conditions required for observers are poorly defined. If the selection criterion is too broad, it predicts little. If it is too narrow, it may mistake local biology for a universal requirement. The cosmological constant offers the most famous example. This quantity represents the energy density of empty space and is associated with the accelerated expansion of the universe. Quantum theory suggests that vacuum energy could naturally be far larger than the observed value, though estimating it is complicated. If the positive value were much larger, expansion might accelerate so early that matter could not gather into galaxies. In a multiverse where the value varies, observers would tend to appear only in regions where it remains small enough for structure to form. The measured value is small, but not exactly zero, making it tempting to interpret as a selection effect. Some arguments based on galaxy formation anticipated a value in roughly the observed range before cosmic acceleration was securely established. This does not prove a multiverse. A deeper explanation may still exist, and the distribution across possible vacuum energies remains uncertain. Other constants present similar puzzles. The ratio between the strength of gravity and electromagnetism influences the scale and lifetime of stars. The masses of the lightest quarks affect the stability of protons, neutrons, and atomic nuclei. The electron mass shapes atomic sizes and chemical energies. The strong nuclear interaction determines which nuclei can bind. Even the difference between the proton and neutron masses matters, because changing their relative stability could leave a universe dominated by different particles. Yet these quantities are not necessarily independent, and a future theory may link them. Varying them casually can produce misleading claims. The careful question is whether a well-defined theory predicts a distribution of consistent universes and whether the observed values are typical among those allowing structure. The possibility of varying laws also complicates the word universe. Traditionally, the universe means all physical reality. In multiverse cosmology, the term often refers to one causally connected domain with a shared vacuum state and a common observable history. The deeper totality may contain regions with different effective physics while still obeying one overarching framework. The diversity is then not lawlessness. It is the expression of a deeper law through many possible outcomes. Ice, liquid water, and vapor behave differently while arising from the same molecules under different conditions. In a much more profound way, cosmic domains may display different particles and forces because an underlying theory settles into different phases. No experiment has confirmed that constants vary between universes. Measurements instead test whether they vary across space or time within the observable cosmos. Established results are consistent with remarkable stability, and claims of variation remain unconfirmed. That local constancy is expected if the vacuum state has remained unchanged throughout the visible region. Other domains, if they exist, are likely beyond direct contact. Their laws cannot be sampled through ordinary light. Evidence would have to come indirectly, through the success of a fundamental theory, signs of bubble collisions, or predictions that make the observed values more probable than alternatives. Until such evidence appears, varying laws remain a serious possibility rather than a discovered fact. The idea draws power from the way modern theories connect particles to fields and fields to vacuum states, but it also inherits the uncertainties of inflation, quantum gravity, and the measure problem. It offers one answer to the quiet balance seen in nature. The balance may not be unique, designed, or inevitable. It may be one habitable arrangement within an immense range, noticed because only such arrangements become capable of noticing anything. Yet even this answer leaves a deeper mystery. Why does the underlying framework possess a landscape at all? Why do its possibilities include stable worlds, mathematics, and self-organizing matter? The multiverse can explain local order through selection from variety, but the existence of the variety still asks for explanation. Beyond the visible universe, the constants of nature may change, stars may never ignite, and atoms may assume unfamiliar forms. Within this domain, the values remain quietly aligned, allowing ancient fluctuations to become galaxies and simple particles to become observers who infer a wider cosmic landscape. Order may emerge because almost every other possibility remains unseen. The universe may not begin from a point, a fluctuation, or an isolated quantum event. In some theories, the hot beginning appears when vast higher dimensional structures move through a larger space and collide. These structures are called branes, a shortened form of membranes. They arise in string theory and related frameworks, where ordinary particles may be tiny vibrations and the familiar dimensions of space may be only part of a larger geometry. A brane can have different numbers of dimensions. One may resemble a line, another a surface, and another a three-dimensional world extended through space. In certain models, the visible universe lies on such a brane. Galaxies, stars, atoms, and light remain confined to it, while gravity reaches into additional dimensions beyond ordinary sight. The larger setting is sometimes called the bulk. It is not empty space in the everyday sense. It is a higher dimensional arena whose geometry and fields follow laws that may differ from those observed within the visible universe. A second brane could exist nearby in this larger structure without appearing anywhere in the sky. The separation would occur along a direction inaccessible to ordinary matter and light. Two branes might pass near one another, move apart, or collide, and a collision could release energy across their surfaces. To inhabitants confined to one brane, that release might look like a hot big bang happening everywhere at once. space would not explode from one central location. The entire brane would become hot and filled with particles, producing the conditions required for the later expanding universe. The collision picture transforms the question of origin. The Big Bang becomes an event within a longer history rather than the beginning of all existence. Before the hot phase, branes move through the bulk. Their approach may be slow and cold. The visible universe, or the precursor to it, can exist in a nearly empty state long before matter and radiation appear. When the branes meet, their motion and stored energy convert into heat. Particles are created, expansion changes, and the familiar cosmic sequence begins. In this way, a collision plays a role similar to reheating after inflation. Both mechanisms convert a hidden form of energy into a hot mixture of matter and radiation, yet their deeper pictures differ. Inflation begins with a field driving rapid expansion within a region of space-time. Brane cosmology begins with extended objects and additional dimensions whose motion produces the transition. One influential version is the ekpyrotic model. Its name comes from an ancient idea of cosmic fire, but the modern theory is mathematical rather than mythic. In the simplest outline, two branes approach through an extra dimension. Their collision creates the hot, dense state associated with the Big Bang. Before the collision, the universe undergoes a slow contracting phase rather than an explosive expansion. This contraction can smooth and flatten the cosmos under suitable conditions. Tiny quantum fluctuations develop during the approach and later become density variations, providing seeds for galaxies. Inflation is therefore not the only known mechanism that can try to explain cosmic uniformity and structure. A carefully arranged contraction may produce some of the same broad results. The ekpyrotic phase behaves differently from an ordinary collapsing universe. Matter and radiation usually grow more important during contraction, and irregularities can become dangerously large. The model instead relies on a component with unusual pressure and energy behavior. Its density increases so rapidly during contraction that it dominates over curvature and many forms of disorder. The universe becomes smoother as it shrinks, not because irregularities are stretched away, but because the special field overwhelms them. The contraction can continue for a very long period while the physical scale changes only modestly. Near the collision, however, the description reaches extreme conditions where quantum gravity and brane dynamics become important. The theory must explain how a contracting phase passes through the violent encounter into an expanding hot universe without producing a fatal singularity. This transition remains one of its greatest challenges. Some models treat the collision as a bounce. The scale of ordinary space stops contracting and begins expanding, while densities remain finite. Others use the higher dimensional geometry to suggest that the apparent singularity in a lower dimensional description is less severe from the viewpoint of the bulk. A shape that looks crushed to zero within the brane may correspond to two surfaces touching and passing through one another in the larger space. Yet the mathematical control of such an event is incomplete. String theory may soften some divergences, but no fully established calculation shows exactly how realistic matter, radiation, and space-time emerge through the collision. The proposal remains a research program rather than a confirmed replacement for inflation. Brane models can also become cyclic. After one collision and a long era of expansion, the branes may gradually separate, slow, and begin approaching again. Another collision then produces another hot phase. Cosmic history becomes a sequence of cycles, each containing expansion, structure formation, thinning matter, and eventual renewal. The cycles need not repeat every detail. Galaxies from one era do not necessarily survive into the next. An entropy, the tendency for usable energy to become more dispersed, creates a serious obstacle. In an ordinary cyclic universe, Entropy accumulates from cycle to cycle, making each new phase different and eventually preventing exact repetition. Some brane models attempt to dilute entropy during an extremely long expansion before the next collision. The universe becomes so large and empty that the entropy within any region relevant to the next cycle becomes very small. Whether this fully solves the problem depends on the detailed model. A cyclic brane universe also faces the issue of stability. The branes must approach in a controlled way, avoid destructive irregularities, and collide with conditions that yield a universe like the one observed. Small differences across the collision surface can become fluctuations, but they must possess the right strength and pattern. Observations of the cosmic microwave background place strong limits on those patterns. Inflation generally predicts fluctuations that are nearly scale-independent and close to Gaussian. Ekpyrotic models can also generate nearly scale-independent variations, especially when more than one field is involved. But the conversion of those fluctuations into the final density pattern may leave distinctive non-Gaussian features. Measurements restrict many simple versions, though they do not eliminate every possibility. Primordial gravitational waves offer another potential distinction. Many inflationary models produce a background of gravitational waves with wavelengths stretched to cosmic size. Basic ekpyrotic models predict a much weaker signal on the same scales. A clear detection of a particular primordial wave pattern could therefore favor inflation over many contracting alternatives. The absence of such a detection leaves room for both, while continued observations narrow the possibilities. The extra dimensions themselves might also leave evidence. Gravity could behave differently at very short distances. High-energy particle collisions might reveal states associated with the bulk, or cosmological evolution might preserve signs of brane motion. No convincing observation has yet confirmed an extra spatial dimension or a brane universe. The mathematical framework remains motivated partly by attempts to unite gravity with quantum theory, not by direct detection. This gives brane cosmology an unusual status. It is not invented merely to tell a dramatic story about colliding worlds. It emerges from serious theories of fundamental physics, yet the leap from mathematical possibility to physical reality is enormous. String theory permits many configurations, and only a small subset resemble the observed universe. A successful model must produce ordinary particle physics, stable dimensions, the measured cosmic expansion, the right primordial fluctuations, and a consistent transition through the collision. It must do so with predictions that distinguish it from inflation and can be tested. Until then, the collision remains a plausible route through the equations rather than an established event in cosmic history. Still, the idea changes the emotional shape of the beginning. The hot Big Bang no longer rises from absolute emptiness. It arrives when two hidden structures meet across an unseen dimension, before stars and atoms, before light moves freely, and perhaps before the present cycle of time. There may be a long approach through a nearly silent bulk. The energy of motion becomes the fire of a universe. A boundary within one description becomes a contact in another. What appears to be creation from inside the brane may be transformation from the wider view. The model does not remove the deepest question, because the branes, the bulk, and their laws still require explanation. It moves the mystery outward into dimensions that cannot yet be observed. The beginning becomes a meeting, and the darkness before it becomes not nothing, but a larger geometry holding worlds apart until collision turns distance into heat. The observable universe is often mistaken for the whole of existence, because it is the largest region that light can reveal. Its boundary appears in every direction, forming a vast sphere centered on the present location. Yet this sphere is not a wall, an edge, or a shell where space stops. It is a horizon created by time. Light travels at a finite speed, and the universe has a finite observable history. Only signals that have had enough time to arrive can be seen. Regions farther away may exist, but their light has not reached the present and may never do so. The visible cosmos is therefore defined not by where reality ends, but by where information ends. This distinction becomes more subtle because the universe expands while light is travelling. The most distant matter now observable is much farther away than a simple multiplication of light speed by cosmic age would suggest. The light begins its journey when the universe is smaller, crosses space that continues stretching, and arrives after the source has been carried to a far greater present distance. For this reason, the radius of the observable universe is several times larger than the distance light would travel through unchanging space over the age of the cosmos. The apparent contradiction disappears once distance is understood as a property of an evolving geometry. Light always moves locally at the same speed, yet the space between distant regions changes during the journey. The horizon has more than one meaning. The particle horizon marks the greatest distance from which any signal could have reached the present since the early universe. The surface of last scattering marks the oldest light that moves freely after atoms form. A different boundary, the cosmic event horizon, separates events that can ever send signals to the future of the present observer from events that cannot, because expansion is accelerating. Some galaxies already seen are crossing into a condition where light emitted now will never arrive. Their ancient light remains visible, but their later history becomes permanently inaccessible. The observable universe is not a fixed collection of objects. It changes as time passes, while accelerated expansion also removes distant regions from future contact. The sky contains both a record of what becomes visible and a quiet map of what is being lost. Beyond the current horizon, cosmologists expect more universe. This expectation does not come from direct observation, because direct observation ends at the horizon. It comes from the simplicity and consistency of the structures seen within it. On large scales, matter is distributed with no clear sign that the visible region occupies a special location. The cosmic microwave background is nearly uniform in every direction. The laws of physics appear the same across the accessible sky. Spatial curvature is measured to be very close to flat. These facts suggest that the observable domain is a small part of a much larger whole. The larger universe could be finite without having a boundary. A sphere has a finite surface area but no edge on its surface. Travelling far enough in one direction returns to the starting point. Three-dimensional space may possess an analogous closed geometry, although it is difficult to picture from within. In such a universe, space curves back on itself. It can contain a finite volume while offering no border and no outside direction. Alternatively, space could be flat and infinite, extending without end in every direction. It could also be flat but finite if its topology connects distant sides, somewhat like a repeated pattern whose opposite faces are identified. Geometry describes local curvature, while topology describes the overall connected shape. Observations can constrain these possibilities, but have not determined the total form with certainty. Searches for repeating patterns in the cosmic microwave background attempt to reveal whether light crosses a finite universe along different paths and returns from multiple directions. No accepted repetition has been found, implying that if space wraps around, its scale is larger than the observable region. The visible patch may look level for the same reason a small field looks flat on the surface of a planet. Measurements cannot prove infinity. They can show only that any curvature or repetition is too subtle to detect within the accessible volume. Infinity remains a possibility rather than an observation. An infinite universe carries consequences that are mathematically clear and intuitively strange. If matter is distributed with roughly similar statistical properties across endless space, then there may be infinitely many galaxies and infinitely many regions resembling the observable cosmos. With a finite number of possible arrangements inside any finite volume, sufficiently distant configurations may repeat. Somewhere beyond any possible journey, a region could resemble the local one with extraordinary precision. Yet such conclusions depend on assumptions about infinity, quantum states, and the uniformity of distant space. They cannot be tested directly. A universe can be unimaginably large without being infinite, and no observation confined to a finite horizon can fully distinguish the two. The phrase beyond the universe therefore requires care. If universe means all space, time, matter, energy, and physical reality, then there is no spatial beyond by definition. Asking what lies outside would treat the universe as an object placed inside a larger container. Cosmology does not require such a container. A finite universe can exist without an edge, and an infinite universe has no outer boundary to cross. If universe instead means the observable universe, then a beyond almost certainly exists in the form of regions outside the present horizon. If it means one bubble within eternal inflation, then other cosmic domains may lie beyond the inflating separation. The same word shifts between three scales, and confusion enters when one meaning is used as though it were another. Nothing in current observation shows a dark external room surrounding all reality. There is also no known center to the entire universe. Every observer sees an observable sphere centered on that observer because light arrives from all directions. This does not place any observer at a privileged cosmic middle. A traveller in a distant galaxy would see a different horizon and a different sphere, overlapping with the local one but extending into regions invisible from here. The centre belongs to the observation, not necessarily to the cosmos. Expansion follows the same principle. Distant galaxies recede from one another on large scales, so each sufficiently isolated observer sees others moving away. It reflects a changing scale between locations throughout space. The horizon also limits knowledge of the early universe. Inflation may stretch once connected regions beyond observable reach, leaving the visible domain as one tiny sample of a much larger inflated patch. Conditions outside the horizon might closely resemble those within it, or they might vary slowly across distances too great to measure. Cosmic variance describes the uncertainty that comes from having only one observable sample. Some features of the universe may result from chance patterns on the larger scales, but there is no second accessible universe with which to compare them. The limitation is not merely technological, it is built into the causal structure of the cosmos. Over the distant future, accelerated expansion may deepen this isolation. Galaxies not gravitationally bound to the local group move farther away, their light stretching toward longer wavelengths and fading. Eventually, distant cosmic structures pass beyond practical and then causal visibility. Future observers may see only the merged descendants of nearby galaxies surrounded by darkness. Evidence of the wider expansion, the cosmic microwave background, and the hot beginning could become difficult or impossible to detect. The present age occupies an unusual window in which the universe reveals both nearby structure and ancient light. The horizon is wide enough to expose cosmic history, yet narrow enough to conceal the full extent of reality. The visible universe may contain every object that can ever influence the present, but it need not contain everything that exists. Beyond sight may lie more galaxies, more empty space, repeating structures, unfamiliar regions, or endlessly continuing geometry. No light brings confirmation from the farthest domains. Their presence is inferred from the absence of an edge and the consistency of what can be measured. The boundary in the sky is therefore not a frontier where existence ends. It is a frontier where evidence grows silent. Space may continue beyond it without limit, carrying histories that never enter any telescope. while the observable cosmos remains a temporary island of information inside a reality whose full size may never be known. A beginning may look different when cosmic history is allowed to turn back upon itself. Instead of expanding from an absolute first moment, the universe may pass through an earlier phase of contraction, reach an extreme state, and then begin expanding again. This possibility is known broadly as a bouncing cosmology. In some versions, the bounce happens once. In others, expansion and contraction repeat through many cycles. The Hot Big Bang then becomes a transition between cosmic eras rather than the origin of all space and time. Their attraction is clear. A bounce can replace a singularity with a physical process. A cycle can extend history before the hot universe without requiring an external beginning. Yet the same models face deep problems. Contraction tends to amplify disorder. Entropy tends to grow. A successful cyclic universe must pass through its narrowest state without losing control of geometry, matter, or causality. The simplest classical picture begins with expansion slowing under gravity. If enough matter exists and no other component drives acceleration forever, the universe may stop expanding and begin to contract. Galaxies approach one another, radiation grows hotter, and density rises. Eventually the cosmos collapses toward a final singularity called a big crunch. If that collapse somehow reverses, a new expansion begins. Early cyclic models imagine this sequence repeating forever, with each big crunch followed by another big bang. The image is elegant, but ordinary general relativity does not provide the reversal. Its equations lead toward a singularity where curvature becomes infinite and the description fails. A bounce therefore requires new physics. Quantum gravity may create a repulsive effect at extreme density. An exotic field may violate conditions that usually force collapse. Extra dimensions may allow a smooth transition hidden from a lower dimensional view, whatever the mechanism. It must become powerful near the critical state and then allow ordinary expansion to resume. Loop quantum cosmology offers one example. It applies ideas from loop quantum gravity to simplified models of the universe. In these models, the geometry of space has a discrete quantum structure. As contraction drives density upward, quantum corrections become important. Gravity, normally attractive, can act effectively repulsive near a maximum density. The classical singularity is replaced by a bounce. A contracting universe passes through a finite minimum size and enters expansion. The result is mathematically suggestive, but it depends on approximations and symmetry assumptions. Whether the bounce remains stable in a complete theory is still uncertain. Another family of models uses matter with unusual properties to produce a non-singular transition. Some require a temporary violation of the null energy condition, a rule linking energy and pressure in relativity. Violating this condition can permit the expansion rate to reverse from contraction to expansion, yet such violations often introduce instabilities or states with negative energy behavior. Newer approaches attempt to achieve a stable bounce through carefully constructed fields or modified gravity. Each solution must be judged not only by whether it reverses contraction, but also by whether it remains physically consistent and produces the universe observed after the transition. Contraction itself can help prepare the cosmos. In ekpyrotic models, a slow contracting phase dominated by a field with very stiff pressure suppresses curvature and disorder, rather than the universe becoming chaotic as it shrinks. The special component grows so rapidly in importance that it smooths the geometry. Quantum fluctuations generated during this phase can later become the seeds of structure. The bounce then converts contraction into expansion and launches the hot universe. This offers an alternative to inflation. Both seek to explain why the observable cosmos is smooth, flat, and marked by small primordial variations. Inflation achieves this by rapid expansion. Ekpyrosis attempts it through slow contraction under special conditions. The two mechanisms can produce different patterns, particularly in gravitational waves and non-Gaussian correlations, giving observation a possible way to distinguish them. A more radical cyclic model extends this sequence indefinitely. The universe expands, cools, forms galaxies, and eventually enters a long dilute phase. A field then drives slow contraction, smoothing the next cycle before another bounce. Each cycle may last far longer than the hot phase familiar to astronomy. The apparent beginning becomes only the latest crossing through a recurring transition. Yet repetition is threatened by entropy. Entropy measures how dispersed usable energy has become, and how many microscopic arrangements correspond to a large-scale state. In ordinary processes, entropy tends to increase. Stars burn fuel, black holes grow, radiation spreads, and structures decay. If every cycle carries the entropy of the previous one, later cycles begin with more disorder. They may grow larger and last longer, making an infinite sequence into the past difficult. Tracing backward leads towards smaller cycles and perhaps an initial one after all. Some modern proposals try to remove entropy from the region that becomes the next cycle. During an extremely long period of accelerated expansion, matter and black holes become separated across vast distances. The universe approaches an empty state dominated by smooth energy. A new cycle may begin within a patch that contains little inherited entropy. Other models claim that entropy continues growing globally, but physical volume grows even faster. So entropy density becomes small. The universe does not reset everywhere. It creates regions where the next cycle begins under unusually clean conditions. Black holes create another challenge. During a long expanding era, they store enormous entropy. Small black holes evaporate through quantum radiation, but the most massive survive for immense durations. A cyclic model must explain what happens to them before contraction, or how their information passes through the bounce. If black holes remain, their density can disrupt the smooth approach. If they vanish, the mechanism must respect quantum consistency. The eventual decay of particles, the stability of protons, and the behavior of dark energy also influence whether a future contraction is possible. Current observations indicate that cosmic expansion is accelerating. If dark energy remains constant, the universe does not naturally recollapse. Galaxies outside bound groups move away forever. A cyclic theory must therefore make dark energy change with time, decay, reverse sign, or arise from a field that eventually causes contraction. No evidence currently shows that such a change will occur. Conformal cyclic cosmology proposes a different route. It does not require the universe to contract physically before a new expansion. Instead, the extremely distant future of one cosmic era is mathematically connected to the Big Bang of the next. As matter disappears and only massless radiation remains, absolute scales of distance and time may lose operational meaning. A vast, cold, expanded universe can then be rescaled to resemble a new small beginning. Each era, called an aeon, follows from the previous one through a conformal transformation that preserves angles while changing scale. Claimed observational traces from earlier aeons remain disputed and have not gained broad acceptance. The model shows how radically the idea of a cycle can change once geometry rather than motion performs the connection. Cyclic theories also confront the arrow of time. Human experience distinguishes past from future because entropy increases. Broken objects do not spontaneously reassemble, and radiation spreads rather than converges. In a universe that contracts, does the arrow of time reverse? Most models say no. Entropy continues increasing even as space shrinks. So contraction does not resemble a film of expansion played backward. Galaxies do not quietly unform into smooth gas. Structures collide, black holes merge, and radiation intensifies. A bounce must carry this arrow through or explain how a new low entropy phase appears. The deepest mystery is not only how expansion begins, but why the early universe is so ordered. Inflation, contraction, and cycles all attempt to address this special beginning, yet none has removed the question completely. A bounce can avoid infinite density while leaving the origin of the prior contraction unexplained. A cycle can extend history while struggling with entropy and stability. An eternal sequence may still require boundary conditions that select it from many possible histories. The past becomes longer, but not necessarily simpler. Even so, cyclic cosmology changes the meaning of cosmic silence before the Big Bang. There may be no timeless void and no isolated act of creation. There may be an earlier universe thinning into darkness, a contracting phase gathering geometry inward, or a previous aeon fading until scale itself loses meaning. The fire of the hot beginning may rise from compression, collision, or mathematical renewal. Every model remains uncertain, but all share a restrained possibility an ending may not be the opposite of a beginning. Under unfamiliar laws, the two may touch, and cosmic history may continue through the place where ordinary time seems to stop. At the farthest edge of cosmology, certainty becomes narrow and carefully bounded. The universe expands from a hot, dense early state. Ancient light preserves a record of that youth. Galaxies grow from small variations in density. Space and time behave as a connected geometry, while matter and radiation shape its evolution. These conclusions rest on observation, calculation, and repeated comparison between theory and the sky. Beyond them, the story opens into several possible beginnings. Inflation may precede the hot Big Bang and stretch microscopic fluctuations into cosmic structure. A quantum state may give rise to classical spacetime. A contracting universe may pass through a bounce. Higher dimensional branes may collide. Eternal inflation may produce many domains, each with its own hot beginning. Cycles may continue through ages of expansion and renewal. None of these ideas stands as a completed account. Each illuminates part of the darkness, and each leaves a deeper shadow behind it. The calmest conclusion is not that nothing can be known, but that the boundary between knowledge and possibility must remain visible. Inflation explains several remarkable features of the universe, yet the field that drives it is unknown. Quantum gravity promises to replace the classical singularity, yet no candidate theory has been confirmed. A bounce can remove an infinite density, yet it must remain stable and preserve the right conditions for later structure. Brane collisions arise from serious mathematical frameworks, yet extra dimensions remain undetected. A multiverse can turn fine-tuning into selection from variety, yet its other domains may remain permanently beyond observation. Cyclic cosmology gives the Big Bang a past, yet entropy and accelerated expansion resist simple repetition. Every proposal gains power from the problem it solves, and uncertainty from the assumptions it introduces. This is not failure. It is the ordinary shape of science at a frontier, where measurement reaches only partway and theory must explore more ground than evidence can yet secure. The phrase "before the Big Bang" therefore holds several meanings at once. It may refer to an inflationary era before the hot thermal phase. It may refer to a contracting cosmos before a bounce. It may point toward a deeper quantum structure from which time emerges. It may be grammatically impossible if time begins at the boundary. The question cannot be answered until the meaning of "before" is chosen, and the correct meaning may depend on which theory survives. Ordinary language assumes a sequence of moments already exists. Cosmology asks whether that sequence has an origin. If time is fundamental, there may be an earlier phase with its own duration. If time is emergent, the deepest state may not happen before the universe in any temporal sense. It may relate to cosmic history as a foundation relates to a building. Not as yesterday relates to today. The explanation would be prior in structure rather than earlier in time. Such a distinction is difficult because thought itself unfolds as a sequence. Every attempt to imagine a timeless reality quietly turns it into a scene that lasts. A dark void waits. A quantum mist trembles. A mathematical possibility remains suspended. Yet waiting, trembling, and remaining are temporal ideas. The mind restores time even while trying to remove it. Physics can move beyond imagery through equations, but equations still require interpretation. A timeless formula may describe correlations without describing a flowing present. A boundary condition may select a whole cosmic history without acting at an earlier moment. A wave function may contain possible geometries without existing inside one. These proposals show that explanation does not always need a familiar cause moving through time, though whether nature truly follows such a scheme remains unknown. Even the word nothing becomes unstable near the origin. Absolute nothing would contain no space, no time, no fields, no laws, no possibilities, and no distinction between existence and absence. Physics does not currently describe such a condition. When cosmological models speak of a universe emerging from nothing, they usually mean the absence of classical space-time or ordinary matter, while retaining quantum rules, mathematical structure, or a space of possible states. That is not the everyday meaning of nothing. It is a highly constrained physical condition. The difference matters because a scientific model can describe transitions among physical possibilities, but it may not answer why there is any framework of possibility at all. Cosmology approaches that question, yet it may eventually meet the boundary between physical explanation and deeper metaphysical inquiry. The boundary need not be a defeat. It may simply mark where different kinds of questions begin. Observation remains the discipline that prevents mystery from becoming fantasy. The cosmic microwave background tests the statistics of primordial fluctuations. Galaxy surveys trace how structure grows. Searches for gravitational waves look for ripples from the earliest eras. Particle experiments probe forces at higher energies. Measurements of dark energy reveal the changing expansion of the universe. Studies of black holes test the meeting of gravity, information, and quantum theory. No single experiment is likely to display the origin directly. Instead, evidence accumulates by ruling out families of possibilities and strengthening others. A particular polarization pattern might support one class of inflationary models. A distinctive correlation might favor contraction. A new particle could reveal the field behind reheating. A quantum theory of gravity might show that singularities are impossible. The frontier advances not through one final image but through a gradual narrowing of what the universe is allowed to have been. Some limits may remain permanent. Inflation can stretch information beyond the observable horizon. Accelerated expansion can remove distant regions from future contact. The surface of last scattering blocks ordinary light from earlier plasma. Quantum uncertainty may place bounds on what can be simultaneously defined. Cosmic variance gives only one observable universe from which to infer the largest patterns. These are not merely gaps waiting for better telescopes. They may be horizons built into reality. Science can still reason about what lies beyond them, but confidence weakens as direct contact disappears. A theory may be elegant, consistent, and compatible with every observation, while sharing those virtues with several rivals. In that case, the universe may contain facts that no observer can uniquely recover. The past would be real without being fully reconstructible. This possibility gives the cosmic beginning a quiet remoteness. it is not only far away in time, it may be partially erased by the processes that follow it. Rapid expansion smooths away earlier detail. Thermal equilibrium destroys traces of initial arrangements. Horizons separate regions forever. The universe remembers enough to reveal a hot origin and the seeds of structure, but perhaps not enough to reveal why those conditions exist. The oldest light is therefore both a message and a veil. Its patterns invite reconstruction, while its opacity hides everything before atoms form. The same tension runs through every proposed beginning. A theory opens one door and reveals another closed behind it. If inflation begins the hot phase, the origin of inflation remains. If a bounce precedes expansion, the origin of contraction remains. If cycles extend indefinitely, the law sustaining the cycles remains. If a multiverse contains every allowed vacuum, the origin of the landscape remains. If space-time emerges from quantum information, the reason for that informational structure remains. Explanation may continue without reaching a final flaw, or it may eventually arrive at a principle so simple that no deeper account is possible. Present knowledge cannot decide. What remains is a universe that is intelligible without becoming ordinary. Its history can be traced across immense spans, from ancient radiation to galaxies, stars, planets, and living matter. Its laws can be expressed with precision and tested across distances no traveller crosses, yet its first foundation remains unsettled. The beginning may be a boundary, a transition, a recurrence, or an emergence from a level where beginning has no meaning. The answer could be one of the current possibilities, a combination of several, or a theory not yet imagined. Calm uncertainty is therefore the most faithful ending. The mystery does not require exaggeration. It is already present in the simple fact that time may possess an edge, that space may arise from something deeper, and that the visible cosmos may be only one region within a greater reality. The journey before the Big Bang arrives at no final scene. It arrives at a quiet threshold where evidence fades, language loosens, and the universe remains open. There, restraint becomes more revealing than certainty, because every honest limit preserves the difference between what the cosmos shows and what it merely permits.